and by then people will join. So thank you very much all for coming to this talk. All of you know the talk will be given by Konstantin Khanin. He is in Toronto, and he will speak about.
I'll give it.
You will give it up. Okay, wonderful. So, yeah.
So
Okay.
the forward title was about transport maps for Random-Durgus equation and the KPZ problem. But it will be transport maps and will be KPZ, but I'll move slowly in this direction. Right? And I was asked this to be a pedagogical talk, and I think maybe not everybody know about KPZ. So I will explain what it is. It's Kardar-Parisi-Zhang. There are unfortunately two KPZ. The same community uses the same KPZ, but two basically different things. Nizhny Likov-Zamolodchikov, it's one KPZ, and Kardar-Parisi-Zhang another. I'm talking about statistical mechanics. It is Kardar-Parisi-Zhang, so I will explain the phenomenon is and how it's related to Random-Durgus equation. But let me start just trying to connect the Durgus equation with the main topic of this workshop, which is turbulence for the Navier-Stokes equation. So this is basically what you will read and people around this for doing a long time. So what is the connection between turbulence and turbulence? And so Durgus equation is a playground when you cannot say much about Navier-Stokes equation or Euler equation. And you work with this. It was introduced a long time ago by Builders. And many questions which are not settled at all, as you can see, you saw today in the talk by Takashi for Euler equation, they're quite well set for the Durgus equation, either with random initial condition or with random forcing. And so what it is? So finite time singularity. $1 million question, and here nobody will give you a penny for that. So it's shocks. So shocks are singularities Durgus equation. They're appearing all the time. It's an avoidable phenomena.
Sorry to be pedantic. Actually, the 1 million problems for Navier-Stokes and viscosity. There's no shocks for problems.
Well, that's what he said.
That's correct. Even less. Yeah, even less than if you add viscosity, then even shocks are not there. So shocks appearing for Euler equation. It should have been $1 million problem. It should be asked about Euler equation, but unfortunately it was asked about Navier-Stokes.
Okay, so which space dimension do you consider?
I will be considering one-dimensional case, but in principle, shocks appearing in any dimension. Well, viscosity is equal to 0. Now, intermittency. As Takashi said today, very strong intermittency. So if we consider structure function, which is we take velocity at point x plus h minus velocity at point x for small h, take it in power p and average it. We take like h in power a depending on p. And this ANP is it's not a linear function. It's a function which is linear until it reaches with the graph of A and P is equal to 1 until 1 goes there, and then it stays on the 1. And this is again very well understood because first, when P is, there are two contributions, one coming from smooth parts of this function U, and another coming when you hit this shock. And shock is a jump discontinuity. So when you hit the shock, it happens rarely, but it will give you contribution, which will be H. That's probability to hit the shock. And this, you always have this contribution. And this contribution will be dominant when P is greater than 1, and will be subdominant when P is less than 1. That will be very strong intermittency. And there is not much to say about it. It's the whole thing.
So your randomness comes from the random initial data?
Well, there is no, there are different settings, but in all the settings, whenever you have shocks and smooth parts of the solution, and then shocks, then you have this type of intermittency.
Sorry, Can you be more specific? I mean, you're talking about many things, and are we talking about burgers with deterministic or with randomness?
Yeah, we're talking about burgers with either random forcing or with even you can consider burgers with random initial conditions. Whenever shocks are formed, you will see this phenomenon.
So that's what.
Yeah. And actually, this dimension one here, shocks are here, just points, and what happened with the interval between this point and this point will hit. So if there is shock in between, probability is small or the H, but when it happens, it will give you a big effect. Right? And the C, it's well understood what does it mean physical big solutions. So it was not clear for us at the talk of about earlier whether these solutions are physical. They're probably not physical. Well, for burgers, it's there are plenty of big solutions. There are no strong solution again when viscosity is equal to 0. In this case, then there is a well-defined physical weak solution. That's called also entropy solution, also called viscosity solution. So it's solution which we obtain in a limit when viscosity tends to 0, and there is well-defined procedure, and I will be talking about it, and formula will be written later. So that's the relation between turbulence and burgers. Now, the singularity is a one-dimensional case, and that will be considered a case when x belongs to R1, the dimension is 1, dimension 1 plus 1 if you take also time. Then, as I said, singularities are points, certain point field, which will be a random field. And so to discuss what's happening on the small distances, it's not very clear what to ask even about this question. But you can still ask important questions, and they're asked normally not in the turbulent community, but the statistical mechanics community. What happened on a global scale? When you look at these shocks and you want to say, what is a global structure? And that will be topic what shall be discussing a lot. And that's where KPZ comes into play. So that is where it comes to explain what KPZ is about. So, there are different ways to describe KPZ. And that's phenomenon which was maybe discovered in the 80s or even before 80s. And we are citing Kardar-Parisi-Zhang, three physicists who wrote the paper about interfaces in dimension 1. But similar phenomena appears in many other settings. The only crucial thing that always happens in dimension 1 plus 1. So two-dimensionality or 1 plus 1 is important here. Otherwise, it's a huge universality of this phenomenon. It's a phenomenon of huge universality. So what Kardar-Parisi-Zhang was considering is more or less the following problem. Not exactly, but it's kind of the following problem. I would describe it in a random deposition setting. So suppose you're kind of building up you're putting random objects on your line at certain times and random positions. And then some kind of bricks on top of bricks and so on. And you fill that thing. And then after a certain time, you get interface between space, part of the space where there is something and empty. And so they were describing this, what you can say about this interface, this graph of this function, which is separating them. On a large scale, on a small scale of this distance ones, there's not much you can say, but if you look at this on a large distance, you modify it, what you can say about this. So they were discussing statistics of this thing. And they saw that this statistic has certain exponents, so certain scaling behavior, which is characterized by numbers 2/3 and 1/3, and I'll describe it in a moment. So that's not what I'll describe. I don't want to describe that. It's a little bit more complicated, but the equation which describes the thing, it is equation what is called KPZ equation. It will appear a little bit later in my talk. Right? Now, how I would describe this phenomenon, I will be more precise, and I will say the following: that I would consider the problem of directed polymers. or sometimes minimize it. So what is the problem? You have Z2 lattice. As I said, it will be dimension 2. One dimension will be time, another dimension will be space. And it will be disordered lattice. So at every point of this lattice, there is a random variable. So it will be I, T. T will stay for integer time, and I will be an integer space. So at every point, you have a random variable. And that's your disorder. So distribution of disorder, there is certain probability distribution of this random variables. Assume they're independent at every point, but distribution of individual one identically distributed, IID, but can be anything more or less, not too crazy. And we fix this omega, so disorder is fixed. And then we want to consider objects in this random potential. So what it means is that we have a lattice. And it's more convenient for me, time will go down maybe. So that will be time 0. At every point, there is a random variable living. And then I start with some point x at time 0. And I want to find, there are two objects. Either I could find minimize. So I want to find curve which can go only to neighbors or to stay the same. So what is allowed to go either to neighbor or to stay the same place. And for this curve gamma, I can define the action of this curve. So this will be the action of this curve will be a time interval from 0 to n for fixed realization of the random variable. This should be sum of these random variables along the curve. So you come and use sum of these random variables. Come to points, add it. And then for giving point, you want to find minimum. For giving x, you want to find minimum. So gamma, which is what they call arc mean. So see, remember this is n here, the final time arc mean of this. So the curve for which this minimum realizes. You want all the possible curves. There are finitely many of them. You just choose one which is as minimum. Basically, it will be unique for fixed n because probability distribution say is continuous. But what you'll be more interested in what happens when n goes to infinity. And it turns out that, and that's not the trivial theorem, and actually the theorem is proved only in dimension 1, 1 plus 1, that when n goes to infinity, this thing will stabilize. So if you had certain beginning of the time for giving n, for larger n, you will respect this beginning. So you have infinitely long minimizers as well. For every point here, it will be infinitely long minimizers as well. Right? So you either look at these minimizers, and this will be minimizer which corresponds to point x, starting at point x at time 0, which exists, but depends on omega, optimization of your randomness. For every point, there is its own minimizer. Or you look on all of these possible curves with certain probability distribution. And that is what's called directed point. So you consider all possible curves, and you say that probability of having a given curve gamma of length n will be proportional to e to the minus beta times action of the thing. So you favor the curves which have small action. And I say proportional because you want probability, total probability to be equal to 1, so it's 1 over partition function times a Gibson factor. That's called directed polymer. So you consider all possible paths, which is kind of simple random walks, but they're not equally probable now. Their probability depends on what are the actions this was.
Still finite polymer.
Say again?
Finite polymer.
It is finite polymer, yes. But actually for polymers also, there's a limit of probability distribution when it goes to infinity. And that's also not trivial theory. Right. So what KPZ says is the following. What kind of questions KPZ answers? It's the following type of questions. Of phenomena. You want to look at the behavior of these minimizing curves or polymers for large n. So fix some large n. And then you can play two types of games.
Assuming that omega is not negative in this.
So it doesn't matter. Because you can always add constant to subtract constant, it will not change the minimizer. It will change the value, but it will not change the minimizer. And statistics will not change by adding or subtracting constant. So it's not essential. You can think that average value is 0. It doesn't matter. So there are two kinds of game KPZ is playing. So basically, I can start, let me still live in a discrete setting. I can play two games. Point to point, or point to line. So for every point here, X, and every point here, Y, I can ask what will be the minimum curve connecting these 2 points. Okay. So the length N in time, the length in time is N. And then you can record the values of the optimal action. So not the path itself, but the value of optimal action. So you record this action. That is an action of gamma, of the optimal gamma connecting X and Y. That is point to point. And another game you can play is point to line. So you're allowed to end up at every point of the line, as long as your length is N, and you still discard the same thing. So then it will be just depending on X only. And this is basically its minimum of the thing over all one. So you look at these two functions, actually it's random processes depending on X and Y, and now you will scale them. So it turns out that if points are nearby, what will happen is that they would connect very soon to be optimal. And the action of them will be almost the same. They will be different by the constant. So if you want to see that the action really varies, you want to look at this on the distances on a scale of the order of n to the 2/3. So if you separate points on a scale of n to the 2/3, then you will see the difference in the behavior. If you take them too close, then it will be small difference, small another behavior, not interesting for you. So that is an interesting scale. I can explain later on why n to the 2/3. Okay? So basically, you look at the following thing. You rescale instead of x, you get n to the 2/3 x, well, x tilde because it will be continuous now. I rescale it, it will be continuous variable when n goes to infinity. And y goes to n to the 2/3 y. And then you take this thing n to the 2/3 x, n to the 2/3 y. You subtract, not interesting, mean value. This mean value will be proportional to n, and that will take care of this constant. So you subtract this constant time n. You also compensate on the fact that if you go from x to y and they're far away from each other, then there are very few paths. So you have to compensate for that. It turns out that compensation is not random. So what you have to subtract here will be, well, let me subtract a little bit later. I will subtract x tilde. So this is x tilde. X tilde minus y tilde squared over 2. That's compensation for the fact that they are far away. But fluctuation of this thing turns out that it will be n to the 1/3. So you subtract the thing, this is a main contribution, constant time n, and fluctuation will be already n to the 1/3. And so actually when n goes to infinity, there is a limiting distribution of this thing already. And we will process depending on x tilde and y tilde. But if you want this process to be a stationary process, you subtract this compensation term, And then when n goes to infinity in probability, this converges to every process depending on x and y. And this is a special process which is universal. It doesn't depend on what was the probability distribution of your disorder. And that's phenomenal. That whatever disorder you put, when you look at these actions, optimal actions, and optimal actions, actually, if you remember what I said about this function separating empty and not empty places, that's exactly the same side. This function A is kind of separation thing. So if you see scale separation thing by n to the third and n to the 1/3, it will converge to the same area process. So this area process depends now on two parameters. And if you play one of these games, then you will have to just adjust it with the 2 points with one game, or take minimum of y for another game, and then you get also universal distribution. But basically, this thing contains all information about it. And this process is stationary. It doesn't depend on any translation. Translation variable. It's a simple fact, but not trivial fact. In principle, it's possible that statistics will depend on points are far away from each other or they're close to each other, but it's not, doesn't matter if you subtract this thing. Now, you also should understand that there are some normalization constant. This is unique up to normalization constants, but I'm not saying about it. Yes.
Do you have the same kind of universal behavior for the Gibbs measure?
Yeah, and that's a very good question. So it turns out that the same type of behavior will be even for Gibbs measure. So when beta is positive. So it's very rare case in statistical mechanics that statistics for zero temperature when beta is infinity and positive temperature is the same. And possible explanation of this is the following, that it turns out that if you look at this directed polymer giving to this measure, it actually is not behaving like diffusion. It's not spreading when it goes to infinity. It's kind of remain localized. So from large distances, it still looks like one path. So random potential in which it develops can be effectively changed a little bit. That still will be one path and some random potential. And statistics will be the same because of universality. So the fact is that it will be universal. Now, the universality is not proven. This is one of the open problems in mathematics, why this is universal. So what is known now is there are a bunch of models for which you use particular distribution of your disorder, of these omegas, and they're kind of integrable, exactly integrable. So then you can calculate many probability distributions related to the thing. For example, 1-point distribution. I said it's stationary. If you fix x, say 0, 0 here, it's just a random variable. And this random variable will have Tracy-Widom distribution. And there are two Tracy-Widom distributions. This in particular, if you fix 2 of them, it will be what is called GUE Tracy-Widom distribution. It's a Gaussian unitary ensemble Tracy-Widom distribution, correspond to ensembles of unitary big Hermitian matrices. I'm not going. This setting also, there are several settings. There is this interface setting, there is this polymer setting, and there is random matrices setting where similar phenomena happening. I choose polymer because they have additional piece of structure, which is geometry. And so what I'm saying is that traditionally people look at this function, action itself. So they record optimal value of action, and they normalize it, and they want to look at the statistics of this process, which is very interesting also. And what I want to look at is the statistics of what's going on with the path, with optimal path which realize this meaning. Okay? So let me play the game of point to the line, and let me try to draw how the optimal path would look like. And what we will see is that, as I said, many paths is glued together. But then it will be some place where it's equally good to go here and to go to another place. So then you'll get another bunch of things which goes to another place. And then another bunch of things. So you'll see that this whole collection of optimal paths, they will concentrate in this thing, in a certain number of points. Now, this number of points will be infinite because it's infinite line. But there will be less and less dense when n goes to infinity. And they're separating here by another point of separation. these points of separation which separate domain going to this point from domain going to that point. Now, there is a general fact connected to the fact that the Hamiltonian here, the Durian equation, is convex, is that minimizing curves cannot intersect. So you get bunch of monotone things. They can glue together or can close together if you're in continuous station, but they cannot go through each other. They will not be minimized. And so because of that, you will see these separation points and points of concentration. And from point of view of where I'm moving now, what is a Burger's equation, the points of separation will be shocks, and the points of concentration will be concentration of mass of a transport problem. And both point fields, this one above and this one below, will get less and less dense when n increases. And the density will be 1 over n to the 2/3. So typical distance here will be n to the 2/3. And typical distance here will be n to the 2/3. Now, what you do in such situation, you have two different, you have this point field with a density which is 1 over n to the 2/3. You want to renormalize it, you multiply it, you just squeeze it by n to the 2/3. So there will be distance order 1 from each other, random distance. And then you want to see what is the statistics of this point field. So what I will be interested in, I will be not looking at the value of optimal action. I will be looking at geometrical objects. So I will take point fields, rescale, by n to the 2/3, and then take limit as n goes to infinity. In terms of distribution. And my point will be that when you do this, you approach certain random point process, universal one, and which will serve all the problems which I discussed here and more. So then, universal linear distribution. Then goes to G. Now, I cannot prove this fact, but I will explain what is the connection of this fact with the Burger's equation, with the random Burger's equation. And then I will also connect with some other things, and I will try to present motivation why I believe it's true and some numerical results confirming it.
So sorry, so you say you cannot prove that, but in the KPZ language, there is this Preyhofer and Spohn, they prove the distributions. So you're saying that you're looking at some universality beyond distributions.
So I know. So Preyhofer and Spohn looked at area process.
Yes.
So basically, this thing they didn't look, but it is basically saying now they calculated the thing for particular model of disorder.
Yes.
It's for the particular integrable model. So when you go beyond particular model of disorder, you change your disorder a little bit, and you know nothing.
I see.
Right?
So which case? It's white noise in space and time?
Well, actually, white noise in space and time, it's a particular case. So let me move to the equations. So the relation, of course, is, so let me have random Burger's equation, random force Burger's equation, and then I have KPZ equation as well. So the traditional setting of Burger's equation is it's velocity field, so it's ut plus u nabla u. You have maybe viscosity times Laplacian, or maybe viscosity is equal to 0, tends to 0, and then I would have here minus f. It will be forcing, random forcing, depend on x and time, like in the Z2 lattice. So I think they're continuous now. Now, this F omega xt is a minus gradient of the potential. Its potential, which is associated with this force section, and then this equation is equivalent to the following. If you introduce what is height function, not height, but height function, and it's equivalent, it's a counterpart of this optimal action. So this height function is related to the fact that gradient of this function, height function, is a space gradient. All these gradients are in space, it's velocity field. So if you introduce this function, then for function h, equation will be Hamilton Jacobi equation. So this is Hamilton Jacobi equation. And, this is goodness. And I will be dimension one mostly, so I can derive its derivative with respect to x, but in general it will be the same thing, right? So the relation here is the following: that whenever you want to solve inviscid case for the Hamilton Jacobi equation, there are no strong solutions. Solutions would have this jump discontinuity for velocity field, and we'll have corner points for the h. So h will be kind of going, and then we'll have corners. That's a reflection of shocks. Because this is a gradient of this function h. So whenever this has discontinuity, this one has corner. And how you solve this equation? There is a variational principle. The variational principle has the following. If I want to solve a Cauchy problem for this equation at time t at point x, I have to consider all paths going down in time, gamma, and for each path I have to calculate this action in random potential, and this will be integral gamma dot square over 2 kinetic part plus f omega x gamma tau and integral d tau from 0 to t. And then you can also add initial condition here. Initial condition will be given to you for this. Your solid problem, Cauchy problem, initial condition given. So you also add this flow at the beginning of this curve and this point. And so you have to take minimum of this thing over all gamma. And this minimum of this thing all gamma is exactly solution at point x and time t. Now the restriction is gamma at time t is equal to x. So if you know where you start, you can end up anywhere, and then you calculate this number, and the minimum of this number gives you something. So that's exactly the same setting as before. So why it's the same setting? Before we were going to nearest neighbors. No, this fact that nearest neighbors is giving me the thing. You cannot go far away because then velocity will be very large, and it's very bad for you. So basically, it's locality of the Lagrangian plus random potential. So it's exactly the same problem, just in continuous setting. And the geometry of this path is more or less the same. It doesn't matter whether there was a lattice or not, because I'm looking what's happening on large times and large distances. So it will look like a continuous path anyway. So that is a connection between random Hamilton Jacobi equation and the problem I discussed before. So basically, they belong to the same universality class, the same setting. Now, it was already said Kapizet equation. It's a particular model, which is actually in many respects integrable, but it's much harder problem from point of view of PDEs. It's a problem where this random potential is not coming from a lattice, but it's actually space-time wide nodes. It's very irregular. And because of that, with this equation, you have a problem. Because this is a white noise. So it is a derivative, basically it's not a function, it's a generalized function. And then you have to take gradient of this thing and take it square. That's not kosher. It's not a good procedure to do so. So that's a difficulty, and that's difficulty which was sorted out by Martin Heidegger and other people, which introduced the notion of, we have a couple of approaches, but how to regularize this problem, how to make sense of this equation. And that was done, and it was Fields medal for Martin Heidegger. But this problem of making sense of this equation for this white noise space has nothing to do with KPZ problem. It is what's happening on small distances that create difficulty. And we're interested in what's happening on large distances. So basically, I would be thinking of this not as a white noise. It will be white noise in time. That doesn't create any difficulty. But I would think that it's smooth in X. So realization of smooth in X, but they may be white in time, that's fine. And then I want to look on the global behavior of these minimizers when time goes to infinity, how they behave.
Excuse me, on the Hamilton-Jacobi equation, this intercept term, is it U or H?
No, to the right, sorry about that.
H.
Thank you. All right, now what this has to do with the transfer problem? So basically, when you solve this equation, you go, there is a set of minimizers.
Can I have a question? Just to clarify. Heidegg's work was for new positive, yes.
Say it again?
Heidegg's work was for new positive.
For new positives, yes.
And you want to consider the equation with mu zero.
It's not very important for me because KPZ phenomena, it has exactly the same formulation and meaning for new positive and new zero. So in my case, it's not, but it's slightly easier for me to discuss equal to zero in this case because minimizer is a slightly easier object than polymers. For example, the fact which I told you that polymers are not getting spread. This is true only in dimension 1 and 2. In dimension starting from 3, they would sometimes spread and sometimes not. There is transition from diffusive behavior to non-diffusive behavior, and that's non-trivial issues. So I'm formulating it, it is settled mathematically. We know that it is localized in dimension 1 and 2, but it's non-trivial fact. Okay. Okay, so let me move to the direction of the transfer problem. So I would. Let's repeat this code. So if I consider solution to Burger's equation, remember that minimizers are kind of bringing their velocity to this point. So minimizers a curve which evolves, and velocity at this point, that's what we will have as a velocity. So a linear velocity at this point, which is solution to Burger's equation, is actually Lagrangian velocity of this curve. And so we have a bunch of this curve for every x. So what we will see is that for every x, there is a curve which is minimizing curve. Now, since we're in continuous setting, we'll not see that they're coming to the same point. They cannot come to the same point, but they can come very close to each other. So what we'll see again, that there's a bunch of curves coming very close to each other. And then maybe there's a shock. When there are shocks, it means that there are two minimizers at that point. And then there's a bunch of curves coming very close here. And then there's another shock, and so on. And so, even though I consider this not for large t, but for time equal to 1, there is a map which takes point here and map it there. And there is an inverse map. Now, for giving time, so these maps are not diffeomorphism normally. What will happen is that 2 points come to the same point here. That's possible. And even it's the way that we have. But there is a map which takes point x and move them to point y. So what happens is that all points within this interval would map to that point. And all points here map here, but otherwise point there has counterpart. So there is map in this direction, and there is map in the opposite direction.
Your map is from bottom to the top, yeah?
I'm mapping from bottom to the top. Here, right? And so what I want to see, what will happen if I would kind of look at this map after many steps. So this map is random, the next map is also random, next map is random, and so on. So I iterate these random maps. And what will happen? And there's a general fact that when you iterate these maps, they would tend to get points closer together. So let me explain this fact, because it's a very simple fact, and it has principle. It's a principal fact in dimension one. Actually, there's a counterpart in another dimension, but dimension one is very. So let me just look at the thing. So I have collection of these maps from I to I plus 1. They take X, and what we can say about this map? So if we start with point X, it's time 1. So the next point will not be very far from X. Right? So the natural thing is that it's X plus something. And this something is order 1. And X can be very large. So we would assume that this thing is a random process. And maybe ergodic process, maybe even on large distances, they are not dependent. So if I look what is behavior for 1x and for very far away x, they're basically dependent. It's decay of correlations. Let me think for a moment that this map is differential. That is diffeomorphism. It's not true, but let me think it's diffeomorphism. Right? So I'm claiming the following thing, that if I take derivative of individual map, and then I take average of this, and I also want it to be homogeneous in X. Transition there. I can take this derivative at any point. Distribution will not depend on which point I choose. And then I take average with respect to omega. I'm claiming that this average derivative is equal to 1. And why is it so? Because if I take a long piece of my x, say from minus L to L, and then I move it by my map, the image, what will be the length of the image? The length of the image, so we can have certain image, and the length of this image will be integral from minus L to L, F prime dx. So if I know the average value of this, then the length will be 2L times the average value. But we know that point is going not very far from this point at time 1. This point going not very far from this point. So the length actually will be of the order 2L plus order constant. So when L goes to infinity, you see that this thing must be equal, the average value must be equal to 1. The only option. Right? That's trivial remark. And now also simple, but not as trivial remark is the following, that now I start to iterate maps. I consider map, which is a resulting map for going from point 0 to time n. And so this will be a composition of, you first do 0, 1, and then 1, 2, and so on, n minus 1, n. And if you want to see how nearby points behave, you have to look what is the derivative of the thing. So you want to take d over dx of this thing. And it will be a product of derivative. Different points, chain rule. And you want to say, well, what does it behave of the thing? So basically, suppose kind of think that at different times these maps are not dependent, or not independent. Best thing independent, think independent. But you can do better than you can consider the situation. So this will be e to the sum of the logarithm of derivative. And so how this sum behave? It behaves like n times average value of the logarithm. Average to the formula. Like before we saw it. But if average value of f prime is 1, then average value of logarithm is less than 1. Is less than 0. But it's less than logarithm of the average value of f prime. That's convex inequality. And that's equal to 0. So you see that necessarily derivative will be exponentially small. So it means that points nearby get closer together, right? But that's not the whole truth, because what happens is, that's principle fact and important for you. It's not the whole truth, because what happens is that if I look at the picture, which we had before, after a long time n, and a huge piece of my X space, I know that, say I took again minus LL, huge piece, this is N capital. In principle, derivative, the map which maps point X to the point Y time N, has derivative, which is of order e to the minus n times some constant c. And c is the average value of logarithm. C is absolute value of this positive number. It's minus sign here. So in principle, it means that this thing would shrink to something which is exponentially small with n. But that's hardly possible because individual trajectory is kind of diffusive trajectory. So it deviates on the distances of the order n to the some power alpha. Typically 1/2, you would think in independent case. But in the case dependent, it's 2/3, which we saw before. And this also comes to something that deviates on the order n to the 2/3. So the distance of the image will be 2L up to this plus something of the order of n to the 2/3, or n to the alpha. And so basically, when L is is huge, this is not this essential thing. I mean, it will be still the same order. But we know that this is very small. So what happens here is that minimizers would have this behavior which we saw before. That many of them would come to a very short interval, then it will be shock, and then many of them will come to the very short interval, and then many of them will come to the very short interval. And so what we will see that there is a shrinkage, but then there are some places which are coming to one point. And so you will see that there are presence of two scales here. There's this exponential scale, which is not very important for me, because I can think this is just one point. And then there's a scale of the distances between the lengths of these intervals and the length of that interval. And that will be order n to the third, or n to the alpha, if it's n to the alpha is a behavior random term. So what we'll see that these minimizers would have this property that they form point fields. We already discussed it, and these point fields can be viewed as a composition of random maps. So it's a random map, and you take composition of them. And basically, you should think of these maps after, if you think that your interval 1 is already large, and you iterate these large pieces, then you can think that they already mapped the whole interval map to this point, and the whole interval map to that point. So the piecewise linear constant maps. So these maps now we should think about something being so that's individual map here. They have again formed x plus something which is homogeneous in x, and they iterate the thing. And what I'm claiming is that what is important here that they're monotone maps. Monotonicity is here because of this shape. So it's already here, monotonicity. And I'm saying that if I know that this thing, deviation of a point under this dynamics is n to the alpha, so suppose I know that if I take point 0 after these n steps, it will be different from 0, and the difference will be order n to the alpha. I cannot say what alpha will be. It can be anything between 0 and 1. But if alpha is given to me, then I'm claiming that statistics of this point field will be universal. That's a conjecture. And we have some results confirming this conjecture. So basically, we can forget about all the setting of previous KPZ. We were looking at all problems which have monotonicity and have non-trivial diffusion constant alpha would have the same statistics of point fields.
Independent of the statistics of F, which was the noise term on your.
Independent of the statistics of the disorder. So everything is determined basically by.
It can't even be white and time.
So it should be decorrelation, certain decorrelation in x and time, and this deviation, and that's it. That should determine. Right? So, and we have evidence for that. So the case which we can study mathematically is the case when alpha is equal to 1/2. That is an interesting case, but it was maybe studied even before.
First year.
Yeah, I think and in this case, when alpha is equal to 1/2, you just choose the thing independently on every step. These maps are independent in time. If you choose these independent maps of this type and start to iterate them and rescale them by n to the 1/2, then you will see universal statistics. And I will describe the statistic in a moment.
So what is it? Is it merging Brownian motion? Something?
Yeah, it is coalesced Brownian motion. So this general statistic will be the following. Process which is called coalescing Brownian motion. It's a Brownian process. You start at time 0 at every point of a line with independent Brownian motion. And when they meet, you continue as 1. So they glue together. Since continuation is independent of the past, it's kind of well defined. You should walk a little bit to define it. What will happen is that although you started from all these points, by time 1, only discrete set of points will survive. So it's a time 1 map of the coalescent Brownian motion. So it means that everyone starting in this interval end up at this point, and then in this interval here, here, and so on. So similar picture. And that is the point field which you will have here, which corresponds to time 1. It has particular distribution. And that will be the fixed point, that everything will have the same statistic as this one. It's trivial that this is fixed, that this thing will not change because of scaling of Brownian motions, non-trivial fact that everything will converge to the same thing, but you can prove it. Moreover, you can prove it with what is the rate of convergence, which is important here. But you can, so that's correspond to alpha equal to 1/2. But now what with numerics which we did is the following. Suppose you take another alpha, which is greater than 1/2 and less than 1. So the point diffuse on the distance n to the alpha rather than n to the 1/2. So that corresponds to what is called fractional Brownian motion. So instead of coalescent Brownian motion, you can consider coalescent fractional Brownian motion. Brownian. You should not be afraid of it. We have the whole problem on fractional differential equation, but basically the following object, that in Brownian motion, increment are independent Gaussian variables. And in fractional Brownian motion, increments are identically distributed but dependent. And they're dependent, and if you take some of them and behave not like square root of their number, but n to the power 2 alpha, where alpha is exponent, what is called Hertz exponent. And so we can see that numerically coalescing fractional Brownian motion with exponent alpha equal to 2/3, but you can consider any exponent. And actually, there are different ways to define it, because there is a memory. Fractional Brownian motions are not Markovian process. They remember, there is a dependence between increments. So they remember the path. So we played several games. One of the games would be that when two things meet together, you just flip a coin and choose one of them to continue. Another game would be to just continue from this point with independent fractional Brownian motion. Both mimic what was done before. Or you can think how much of space already collided at that point and give preference to one which has more mass on it. So we played several games of coalescent fractional Brownian motion, and statistics of point fields which we are obtaining was the same as KPZ numerically, and the same for different games we're playing.
By memory, do you mean persistence of the direction or what? What do you mean by memory?
Memory is the following, that, as I said, in normal Brownian motion, if you consider increment, so the difference between this point, and so on, the increment of the Brownian motion, they're dependent Gaussian random variables.
Yes.
And now these increments form a sequence of Gaussian random variables, which are identically distributed, but they're dependent. They have correlations. Oh, and that depends on alpha. So the memory loss is 1 over distance in power alpha. So that is dependent on this exponent alpha. So you have to choose particular. So there is particular correlation function between them. It's a formula, very simple formula for the correlation. Basically, yeah.
But Rama, you're working on kernels, historic kernels. It's very similar, except that you apply it to the Brownian motion.
Okay.
So you integrate over the past with the proper kernel.
Yeah, but if my next step has to depend on my past, in Brownian motion, I randomly choose, right? But now you're saying I'm persistent, I persist. Is that what it is? Like I take some average of my past and I
that you
decide
implement
what
even on your past.
So like that's amounts to persistence.
Yes.
Okay, and so we see numerically that the point fields will have the same statistics. Problem coming from what is called last passage percolation, the problem I described before, KPZ problem, and these problems, which is not KPZ problem, because we don't know how to associate height function or area process to this process. Only geometrical objects are the same. We see the same statistic. So statistics is determined basically by monotonicity and the displacement. So if you know how far you go and they are monotone, there is only one statistics which is consistent with this information. And that's what we see. And so this is enlargement of the class of universality class for KPZ. And also explaining that a lot of this universality in terms of geometric object is coming not from maximization and minimization, but just from monotonicity, which is there because of the maximization and minimization. And then the strategy of proving universality for KPZ would be the following: that the fact that alpha is equal to third, it's well understood fact. It's established fact. We know it. Now, if we establish that geometrical objects have the same statistics for giving alpha, then it's a lot of universality. And after that, you want to establish that there is only one statistics of the Airy process, which is consistent with this statistics of geometrical objects associated to it. And that's another problem which we are not discussing. So that's state of art here, looking at KPZ problem not from point of view of the interface function or action of the optimal path, but on the geometry of this optimal path, how they get together, and what is the statistics of them getting together and being separated. Let me finish here.
Thank you very much. Questions for Kostya? Sure, we'll be happy to answer.
What about alpha less than 1/2?
Alpha less than 1/2, so the fractional Brownian motions, they have two bunches, less than 1/2 and greater than 1/2. And greater than 1/2, they're positively correlated. So it means that if you had one displacement before, then it tells you that it's likely that you go the same way. And alpha less than 1/2 are anti-correlated. And they're different in a sense. So I'm not discussing alpha less than 1/2. I mean, that issue. It's an interesting question, but I don't know.
The closest thing to turbulence will be alpha 0, alpha equal to 0.
Well,
Not correlated the trajectories.
yes. So it's a good point. We want to think about this alpha greater than 1/2.
Any chance to connect really with Euler-Navier-Stokes, because here you start with velocity gradient, which is basically, we know that that's not the case in Navier-Stokes, because the gradient is the pressure and it's divergence free. So all this structure with the variations, is there any chance to connection? It looks like it's the orthogonal problem.
It is not connected to two. First of all, it is very one-dimensional.
Understand?
And this is seriously one-dimensional. Now, there are very interesting questions what will happen in this type of problems in high-dimensional case, 2 and 3 in Burgers. That is one thing. Now, of course, it's Burgers, it's not Navier-Stokes, it's another problem. So I would not, like Takeshi said, there are not much of physical insight in the turbulence behavior coming from this. It's more like global structures coming of shocks, and this is very much in area of interest for statistical mechanics and this type of question. But if you learn something in this talk, although it's not turbulence, I will be very happy. Right?
Any other questions?
Anything on the crowd of people on the Zoom?
Oh, great. Thank you for remembering.
I would expect no, but
Well, I usually do.
There's only me. There's only me, and I don't have any questions.
Okay.
I was okay.
Everybody else left. There was a couple more people, but they're gone now.
Yeah.
Okay, fine. All right.
Have you tried, if, I don't know if it makes sense, coalescing Levy process?
No, we didn't. And we're coalescing fractional Brownian motions, but not because we're nasty people, because we're forced to do it by the KPZ problem. So we do it because KPZ behave with non-standard diffusion, and that was a natural candidate to check whether. By the way, the object of coalescing fractional Brownian motion, strangely enough, it was not considered in literature before. We didn't find any mention of coalescing fractional Brownian motion, and actually we are finishing our paper where we want to prove that this process exists. They should exist, but dealing with fractional Brownian motion is a difficult problem because it's non-Markovian. And it's create anything in non-Markovian create difficulties, mathematical difficulties. And you have to kind of overcome them. There are no doubt it exists in any setting we consider, but proof is not simple.
Okay. On that note, let us thank Kostya again. Thank you for coming to the talk. So, tomorrow. There's no talk. There's no talk. No. Tomorrow there's no talk time. Okay.
If you want, you can.
No. I think next week we have several talks.
Actually, we course, the skills reflections by
Yes.
and actually for those who are interested